Hello, everyone. Welcome to Paul Allen School Colloquium. It's my pleasure to introduce today's speaker. Xinyun Chen is a PhD candidate at UC Berkeley, advised by Dawn Song. Xinyun has been doing great work in program synthesis from the angle of applying machine learning, specifically building synthesizers on top of deep networks. She also did sort of the dual of that, adding symbolic methods to deep networks. And she'll tell us all about this and her future work in the talk. Thank you for joining us, Xinyun, and we look forward to the talk.
Yeah, thanks a lot for the introduction. And also thanks everyone for attending my talk. I'm very excited to meet all of you and share my research on learning-based program synthesis. In this talk, I will discuss my research on learning for program synthesis applications and program synthesis for learning problems. First, what do I mean by program synthesis? Basically, instead of writing all the code ourselves, we want to ask the machine to automatically generate programs according to our descriptions. My long-term vision of program synthesis is to democratize programming so that general users without coding skills can also benefit from all the advancement of programming technologies to automate their tasks. Program synthesis has already driven numerous applications, and I will mention some of my works as examples. Automatically translating natural language descriptions into programs is important for end-user programming. For example, I've worked on synthesizing if-then programs from natural language commands. Basically, given a user-written sentence, such as auto-save your Instagram photos to Dropbox as shown on the slide, the synthesizer can generate an if-then statement to connect the corresponding API calls from Instagram to Dropbox. This program paradigm has been used in various companies for workflow automation. For example, IFTTT includes around 20 million users and supports over 700 API services so far. Another program specification format is input-output examples, which is commonly used in many programming courses. For example, I've worked on synthesizing programs in educational programming language called Carol. And Carol language suite has been used in some introductory CS courses, such as CS106A at Stanford. We can also synthesize programs from multiple data formats simultaneously. For example, my work on data visualization shows that our model can predict the Python visualization code in Jupyter Notebooks, given the natural language markdown and preceding code blocks. Last year, my work Spreadsheet Coder enabled spreadsheet formula prediction from a tabular context. This model was integrated into Google Sheets with hundreds of millions of users. Program synthesis has been a long-standing challenge, and its history can be traced back to the 1950s. Then, why should we bring learning-based techniques into the program synthesis field? Here, I will discuss some modern program synthesis applications as examples. One of the earliest widely used program synthesis systems is FlashView for Microsoft Excel spreadsheet auto-completion. It considers each spreadsheet data row as an input-output example and synthesizes a string translation program in their domain-specific language or quantity. This system relies on symbolic search to generate programs, and the input-output examples need to be fully accurate. Starting from around 2017, some neural network architectures emerged for FlashView, which allows the model to generate programs even if there are some typos in the input-output examples. My spreadsheet coder work last year further enabled spreadsheet formula prediction from ambiguous tabular contexts, and you can even generate some conditional statements. From the progress of program synthesis for data processing applications, we can see that learning-based techniques support noisy and ambiguous program specifications by capturing some common patterns in the training set. This is hard to achieve with pure symbolic approaches, because handling each different type of noise and ambiguity in program specifications can require very different heuristics, and defining all of them manually requires tons of human effort. We can see a similar trend for natural language applications. Before 2016, the dominant approaches for program synthesis from natural language explicitly learn the grammar alignment between a natural language and a programming language, or they are adapted from statistical machine translation. These approaches are generally hard to scale to more complicated languages. In 2016, my work, among others, on if-learn program synthesis shows that neural networks are much better at handling noisy user-written natural language descriptions. Then in the past 5 years, our community is making great progress to support more and more complicated languages, such as nested SQL queries, as shown on the slides. More recently, DeepMind released AlphaCode, and I was part of the team when I entered there. This work shows that with large language models and large-scale program sampling, AlphaCode can achieve approximately the level of average human programmers on competitive programming. So in general, learning-based techniques support more complex program synthesis domains and inspire new applications. And these associations also hold for many other association formats, such as images. So I have been working on learning for program synthesis since the very early stage of this field, which is around 2016. Here I will give an overview of my works in this space, and I will discuss them along 2 dimensions, which are the input ambiguity and the program complexity. The input ambiguity means whether the program description is precise enough to specify the program execution behavior. And the program complexity means the length of a program and the control flow structures that can be correctly synthesized. In my work on programming with text, the main challenge is to handle the input ambiguity, as user-written natural language descriptions usually lack enough details. For program example problems, the program execution includes input-output examples, so it is easier to utilize execution results to scale out the program search. For competitive programming, the program description usually includes both natural language and input-output examples, which further reduces the ambiguity of executions and allows the model to synthesize more complex programs. Finally, when a program functionality is described as another program, such as in the cases of code translation and code optimization, the program execution is more precise, so we can consider programs of even higher complexity, including real-world large projects. Besides working on learning for program synthesis applications, another line of my research is program synthesis for learning, where I consider the program as a means of representing problem solutions for broader learning problems. So why is it beneficial to learn program representations beyond programming and software engineering applications? The main motivation is because existing deep neural networks are still insufficient for handling some important challenges in artificial intelligence and machine learning, including symbolic reasoning and generalization. On the slides, I'm showing a concrete example of learning binary addition, where the models are trained on inputs of lengths less than 20 and are tested on inputs that might be longer. For most humans, we can easily generalize the knowledge of adding smaller numbers to add larger numbers. However, existing language models quickly fail on larger numbers, showing that the model has a hard time precisely learning symbolic operations. So my works on program synthesis learning aim to address these challenges. It adds an additional dimension to my research, which is generalization in a programmatic way to test samples that are out of the training distribution. My works in this space include natural language understanding and conversational generalization. In this talk, I will highlight 3 lines of my works focusing on these 3 dimensions of program synthesis research. First, my work Spreadsheet Coder predicts formulas in user-written spreadsheets that typically have ambiguous descriptions. It shows the production impact of learning-based program synthesis techniques. In my work on execution-guided program synthesis, I demonstrated with input-output examples in the program execution, modeling intermediate execution states improves the capacity of programs that can be synthesized. Finally, my neural symbolic work shows that incorporating symbolic modules into deep neural networks is important for symbolic reasoning and generalization in some challenging language understanding domains. So let's get started with the first part of my talk about spreadsheet coder. Here is a simple demo to illustrate how spreadsheet coder works. Basically, when a user types the sum operator, it means that the user is going to write a spreadsheet formula. In this case, spreadsheet coder will be activated to provide some formula suggestions. As you can see, users do not really write down very explicit descriptions about the formulas they want. But still, spreadsheet coder is able to predict formulas that fit pretty well into a tabular context. Spreadsheet language supports a wide range of formulas. In the previous demo, we've seen examples of numerical calculation. Besides that, spreadsheet coder also supports conditional statements, formulas for table lookups, etc. In total, there are around 100 commonly used special operators called by spreadsheet coder, which is a pretty comprehensive set. We started the spreadsheet coder work as a research project. And later last year, we integrated spreadsheet coder into Google Sheets, which can benefit hundreds of millions of users. As mentioned in a couple of news titles, our formula suggestion model acts like autofill for math, makes data analysis quicker, and reduces the burden of learning and memorizing the spreadsheet language syntax. Predicting a variety of formulas for user-written spreadsheets in the wild introduces many new challenges. The first challenge is to understand complicated spreadsheet data in different formats. Specifically, the model needs to understand table headers, which are usually natural language descriptions of the spreadsheet data. It also needs to understand the actual cell values, which can be numbers and string literals. The second challenge is to understand the spreadsheet structure. So spreadsheet formulas do not always operate on a single row or a single column. Instead, the cell references can range on multiple rows and columns simultaneously. Therefore, it is beneficial to represent the tabular structure of a spreadsheet data. However, spreadsheet tables can be pretty large. On the slides, I'm showing an example where there are over 11,000 rows in a single table. Therefore, if you want to encode the tabular context for formula prediction, then a major challenge is to model the long-range dependency of different cells, which can be far away from each other in the input table. So facing all these challenges, there are several goals we want to achieve with the neural net architecture design. First, the model needs to embed different input data formats, including natural language, numerical values, string literals, etc. The model also needs to represent the input tabular structure while modeling the long-range dependency of the input data. And finally, the model needs to be able to decode various formulas. With these goals in mind, our problem setup is that the model input includes both the table header and surrounding cell values. Then the model output is the spreadsheet formula. Now I will discuss the key design of our spreadsheet coder architecture, with a focus on modeling both the input and output structures. At high level, our spreadsheet coder architecture has two key components. One is the encoder, where we consider spreadsheet data as a semi-structured table. Another component is the decoder, and I designed a two-stage decoding process to generate formulas. So now I want to go into the discussion of some building blocks in this neural net architecture. The first building block I want to discuss is this BERT encoder. So BERT itself is a neural language model, which takes the input as a token sequence and then produces contextual embedding vectors for all the input tokens. We can also adapt this encoder to handle the input tabular data. So in this case, we concatenate several rows or several columns into a single sequence. Then we feed this concatenated sequence into the encoder to compute their embedding vectors. However, as I mentioned before, the full spreadsheet tables can be pretty large. So it is computationally expensive or intractable to compute embedding vectors for all the cell values at once. Therefore, to enable this encoding of large tables, I designed a two-stage encoding procedure. In the first stage, I split the entire table into multiple blocks, and there are two ways to do this split. One way is through row-based encoding. So here, each table block includes several rows. Then we scan through the entire table to obtain this row-based block embedding. Another way to do this split is through column-based encoding. So this time, each block includes several columns. Again, we scan through the entire table with this block to obtain our column-based block embedding. In our full encoder, I include both the row-based and column-based components to represent diverse local tablet structures which can occur in user-written spreadsheet tables. Then I want to discuss the second stage of this encoding procedure, which includes this row-wise and column-wise convolution. The motivation of designing these one-dimensional convolution layers in the encoder is to model the long-range dependency. So let's revisit this row-based block embedding, for example. If we look at cells in different local blocks, then we can see that changing the value of one cell doesn't change the contextual embedding vector of another cell, which means that this dependency across different local blocks is not represented in this block-wise embedding. So to address this limitation, here's how these one-dimensional convolution layers can help. So on the slides, I'm showing this column-wise convolution as an example. So here we have this convolution kernel, which spans across different local blocks within the same column. So once we scan through these different cells with this convolution kernel, we obtain another version of table embedding, which then also represents this dependency across different local blocks, but within the same column. Then with this same convolution kernel, we can compute the embedding for the full table. So in our final embedding, each cell contextual embedding vector can represent this dependency for cells both within the same block and also across different local blocks. Then for formula prediction, I designed a two-stage decoding process to model the output formula syntactic structures. In the first stage, the model decodes the sketch, which includes both spreadsheet functions and literals. Then in the second stage, the model decodes the ranges, which are relative cell references as the arguments to the spreadsheet functions. For evaluation, here I'm presenting the results we also published at ICML last year. So here we train and test all the models on a small subset of spreadsheets available in the Google Sheets team, which already has around 20 million row formulas. We define our formula accuracy based on a syntactic match, which requires the full predictive formula to be syntactically the same as the ground truth. First, we can see that our full model achieves over 42% top one accuracy, which we find high enough to be practically useful. Then for comparison, we also evaluate variance of our spreadsheet coder model with missing components along with other baselines. So from all this comparison, I mainly show that modeling the tabular structure of the input spreadsheet data as well as the output formulas really improves performance. Then in the second part of evaluation, I demonstrate the importance of understanding the input data with different formats, especially the natural language contents in spreadsheets. Here we can observe that headers play a critical role in achieving a good performance, which shows this importance of understanding the natural language descriptions. And as you can see from a simple example shown on the slides, headers can really be very important, and also it makes it easier for prediction in many scenarios. So this idea of two-stage coding for modeling the output syntactic structures is not only designed for spreadsheet languages, which is more domain specific. We can also extend this idea to handle more general purpose programming languages. Here, I want to briefly introduce another application of visualization code synthesis, where our goal is to generate programs in Python. So here I'm considering the program environment of Python Jupyter notebooks. And the goal is that we want the model to generate programs for visualization given the preceding natural language markdown and the code blocks. So in our plot code architecture here, again, the encoder needs to embed multiple input data formats, including natural language and code context. Then in the two-stage coding procedure here, the sketch includes the visualization libraries and function calls. Then in the second stage, the model decodes the plotted data, which are typically Python data frames and variable names. Empirically, we evaluated all our models for a collection of Python Jupyter notebooks crawled from GitHub. So this is built upon a prior benchmark called JUICE, and then we extract especially visualization code from this benchmark. On the slides, I'm highlighting these population studies of two-stage coding. Again, I show that this modeling of the syntax structures is very helpful for improving the performance of synthesizing this code written by real users. So to summarize, in the first part of my talk, I show that modeling the structure and multimodality of these program specifications can really enable real applications with ambiguous program functionality descriptions. So this program syntactic structures is one information we can utilize to better understand the programs. I see there's a question.
If you don't mind, since it is about the spreadsheet work, otherwise
yeah,
you're
sure.
welcome to push it off until later. You really focused here on synthesis and predicting formulas given all of the context in the spreadsheet. Have you tried to use the same model to detect likely bugs in spreadsheets? And if not, do you think it would be effective, or is there not enough accuracy yet?
Yeah, this is a great question. So definitely the same model might be applied for that purpose. So basically we can again like mask out some formulas, and then we can see whether the model prediction matches that. I didn't like do this evaluation for this specific work, but I think one challenge here is definitely about like how you will specify what can be the bugs here. So basically, when the model predicts something different, so how can you be confident that this is indeed because the initially written formula is wrong, or is it because there are just some ambiguity here? So in terms of this like prediction confidence part, I think there are still some works that we need to do to make sure these predictions can be we can like I think this can be modeled using some prediction scores, but indeed there will be need some more works here to validate whether this is empirically effective.
That makes sense. I agree. Thank you.
Yeah, thanks for the question. So basically, in the second part of my talk, I will discuss about how can utilize another information of these programs to better understand the semantic meaning, which is about program execution. So in this part, I will focus on the problem setup of input-output program synthesis or program by example. So here, the program specification will include several pairs of input-output samples. And the model will generate the program to transform these inputs to the outputs. On the slides, I'm showing a domain called Carol. So Carol is an educational programming language that has been used in some CS courses, such as Stanford's CS106A. So before I go into any discussions of the program synthesis algorithms or the neural net architectures, I want to first introduce this language and see what are some challenges of generating programs in this domain. So in the Carol domain, all these execution states are two-dimensional grid words. And Carol is this robot in a grid world, so the program is about controlling this robot to perform some actions in this simulated environment. Another concept I want to introduce is this obstacle. So the Carol robot cannot pass through these obstacles during its navigation. There are several actions that we can execute within this programming language. So basically, move means that the robot can move one step forward. put marker means the robot can put one marker in the current grid states in. So here, these gray dots are markers. Then similarly, pick marker means the robot can pick up one marker in the current grid states in, and turn left and turn right about changing the directions to move forward. Besides the actions, the Cairo language also defines some conditions. So from is clear checks whether the robot is able to move one step forward. Marker presence checks whether there's any marker in the current grid states in. Then left is clear, right is clear have similar semantic meaning to from is clear, but they check different positions in the grid word. With this definition of these actions and conditions, then we can also write some control flow constructs in the Cairo language. And this is the core challenge of synthetic programs in this domain. Specifically, with the Cairo language, we can write down if-else statements and also some loops, including the repeat and while loops. With this discussion of the language, now I want to introduce the standard neural net architecture for these improbable program synthesis problems and see what are missing here. So again, the standard neural net architecture for this problem follows the encoder-decoder framework. So the encoder will compute embedding vectors for the improbable samples, and the decoder generates the program as a token sequence, so step by step, token by token. This is a reasonable framework to start with. But the main limitation here is that with this program setup of directly generating the program from the improbable samples, this model doesn't utilize this execution effect of these generated program statements. So let's recall that when we introduce the actions in the Cairo language or the program statements in general, so all of these statements have well-defined semantic meaning and they make deterministic changes to the execution states. But we simply formulate this program as to directly generate a program from the program specification, then this formulation doesn't take this execution state transition into account. So as a result, this model simply represents the program as a token sequence. So it represents the syntax of the program, but not the semantic meaning. To address this limitation, I designed an algorithm called execution-guided neural program synthesis. And I will illustrate the core idea of this algorithm with a simplified example shown on the slides, where I assume that there's only one improbable pair in the program specification. So at the beginning of this synthesis procedure, still we have these initial improbable samples as the model input. But then every time when the model predicts a program statement, such as put marker here, with the execution-guided synthesis, this program statement will be immediately executed and results in a change of the current state. So that at the next time step, this new state will be fed into the model and guides the subsequent synthesis of the program. So in this way, we can better leverage these intermediate execution results, which provide more information to the synthesizer about what is the current progress made by these generated program statements, and also what are the remaining statements that might be needed to transform from the current state to the target state. In general, utilizing execution allows the model to generate longer programs more accurately by really using these execution traces, which provide some milestones for the synthesis procedure. So from this example, I demonstrate how we utilize execution to generate straight-line programs, which means programs without complicated control flow structures. We can further extend this idea of execution-guided synthesis to execute conditions, which then also allows us to generate programs with branches. So for example, every time when the model predicts a condition, we will first execute this condition on all the given improbable samples, so we can split them into two subsets, one for the true branch and one for the false branch. Then we feed these two subsets to the synthesizer and generate the two branches respectively. And finally, we combine the predictions of two branches together to form these full statements. So in this way, with this execution of both conditions of also other program statements, we can generate programs with if-else structures and also for other structures such as while loops. So far from this discussion, I actually make an assumption, which is that we assume that there is an interpreter available to generate these intermediate execution states precisely. But in practice, there are also many programming languages where this interpreter is not available. So in these scenarios, I propose to learn a neural module to approximate these program execution states in the latent space. So you can still leverage these execution results to guide the synthesis procedure. So this is what I call the latent program execution. With this idea, I designed a new program synthesis framework called latent program synthesis. So in this framework, there are two core neural components. The first component is this program decoder. So again, we can use a standard language model to generate the program token by token. So this component mainly aims to check the syntactic structures of programs, but it is not explicitly designed to model the semantic meaning. On the other hand, with this newly added latent executor, it aims to approximate the program execution, so it attempts to understand the semantic meaning of these generated program statements. With this data executor, the main challenge is to want to train this neural module without any supervision on intermediate program execution states. This training signal itself is hard to obtain. But at least for these standard and typical programming languages, we have the ground truth execution results of full programs. So you can use these full program outputs as the training targets for these execution states at the last time step. Still, this training objective itself doesn't directly provide a supervision on these intermediate execution states. So our solution here is that we will construct a training set to include both short and long programs. So in this way, we aim to have the model to learn these intermediate execution states in long programs approximately by learning the execution results of short and complete programs. Empirically, I demonstrated our execution-guided program synthesis approach outperforms all the baselines that do not model the program execution. And I show this performance improvement on both Carol domain-specific language with interpreter, and also C language for more restricted this processing domain where there is no interpreter available. So to summarize, in the second part of my talk, I show that modeling these intermediate execution results improves the capacity of programs that can be synthesized from improper samples. So in the first two parts of my talk, I mainly discuss how you can utilize some auxiliary information of programs to better understand them and also to improve the performance of learning-based program synthesizers. Then in the third part of my talk, I want to introduce another line of my research on program synthesis learning, where I will demonstrate how you can design these neural symbolic frameworks for language understanding. So in this part, I will focus on the problem setup of question answering. So here, the model input includes a question and also a passage which serves as a context to answer the question. Then the model output is the answer to the question grounded on the passage. For the example shown on the slides, this answer is a span extraction from a passage. And actually, such span extraction-based question answering have been pretty popular in the literature of natural language processing. So there have been some standard architectures developed for these question answering problems. Typically, these architectures also follows this encoder-decoder framework. So for the encoder, we can use a pre-trained language model to compute embedding vectors for all the input tokens. Then the decoder is another neural module or neural layer to directly generate the final answer. The ground truth answers are provided in the training set, which can be used for supervised learning. Such a model design has been working very well on some standard benchmarks. For example, on SQuAD benchmark for reading comprehension, language models have surpassed human performance a while ago. More recently, from these results of this gigantic OpenAI GPT-3 model pre-trained on a giant text corpus, we can see that even without fine-tuning on a specific data set, this model might still perform pretty similarly to those fine-tuned models, such as the case on trivial QA dataset for question answering. So such impressive performance of these pre-trained language models have been driving people to think where the large-scale pre-training is just all we need for reasoning over natural language. However, as I mentioned at the beginning of the talk, existing language models are still insufficient for some more complicated questions that require precise symbolic computation. For example, on the slides, I'm showing a arithmetic question where the model is required to manipulate different numbers in the passage. So following the standard question answering problem setup, in the training set, the ground truth answer is provided, but this explanation is not. Here, I want to argue that if we do not change the problem setup, then pre-training alone will not be sufficient for handling these problems. Because for such problems that require symbolic computation, directly generating the final answer as a token sequence is just not the right approach. The model really needs to rigorously perform this multi-step derivation to obtain the final answer. Similarly, for counting questions, the model needs to first extract relative spans in the passage and then do a counting over them. And for multi-span extraction questions, the model needs to iteratively extract relative spans in the passage to form the final answer. All the examples I just mentioned are drawn for a reading comprehension benchmark called JOP, which emphasizes discrete or symbolic reasoning over paragraphs, especially numerical reasoning. Therefore, if we naively rely on pre-trained language models, the F1 score is at most around 36, which is clearly below human performance. So the key message I want to convey here is that pre-trained language models are definitely important, but they themselves are still not enough yet for symbolic reasoning. So to really perform symbolic reasoning over text, I propose the neural symbolic reader framework. The core change lies in this decoder part. Specifically, instead of asking the model to directly generate the final answer, I designed a programmer module as a decoder to synthesize the program, so that after we execute the program, it can produce the answer. Compared to standard question answering frameworks, the core change introduced here is that we need to train the model to generate the programs without any ground truth program notations. So this means that our programmer module needs to learn this prediction channel only given the final answer during the training time, and all this reasoning procedure will be represented as a compositional program. With this program setup, there are two challenges emerge. The first challenge is to design the program space so that it is expressive enough to cover a broad scope of problems. Then the second and more important challenge is how to train this model without any ground truth program notations. To deal with the first challenge, here's where our domain-specific language design comes in. So the core design principle is that with this domain-specific language, it allows the composition of different operators, which really allows this language to cover a very large space of these problem solutions. For example, we can compose different math operators for arithmetic questions. We can compose different span extraction operators for multi-span extraction problems. More interestingly, I also introduced these span extraction operators as the basic operators to select the arguments, so that this composition can lead to some more advanced functionalities, such as counting and sorting. Then with this introduction of the language, the next challenge is how we can train our model with weak supervision, where we only have the ground truth answer, but do not have the corresponding programs for training. There are two challenges related to this training problem. The first challenge is that the program subspace can be exponentially large to provide a training supervision, especially for programs with nested operations. So let's consider this question: who kicked the longest field goal? And the answer is George Scobie. So given if this is a training problem, they want to search for corresponding programs leading to this ground truth answer. But for this specific kind of problems, even we already know that this is a sorting problem, which means that we know the ground truth operator. Still, the ground truth answer only tells us about one key value pair in the argument, but we know nothing about other key value pairs to compare with. In this case, the search space of possible programs grows exponentially to the passage length, which is intractable when the passage becomes longer. Furthermore, even for those categories of questions where it is easier to find some possible programs, there's still another issue of spurious programs. In particular, for questions with the scalar answers, typically there can be many different programs using different operators, but all of them lead to the same execution results. Among all of these programs, typically only one of them is semantically relevant to the question, and all the remaining programs are spurious because they result in the same the correct answer for wrong reasons. But since all of them have the same outputs, then without manual annotations, it is challenging for the model itself to really tell them apart. So to address these limitations of weak supervision, I designed a training algorithm called hard expectation maximization with thresholding. So this hard EM component was also proposed in prior work to deal with the spurious programs issue for weak supervision. So the issue here is that the model prediction confidence can indicate the program correctness. So we want to use programs with higher prediction scores as the tentative training targets. Meanwhile, with this thresholding procedure developed in our work, I aim to really automate this program search for larger program space with more operators. So the key insight here is that we can further utilize this model prediction score to indicate the program capacity. In these ways, we can automate this training curriculum design without manual investigation. So with this discussion of the approach, here I want to demonstrate some results. On the job benchmark, I demonstrated our neural symbolic reader achieves a state of the art at the time of submission. And it outperforms other neural networks that employ separate classification modules for different types of questions. And in particular, here I show that for those categories of questions where this composition is very important, the model performance improvement is also more significant in these cases. Furthermore, with our neural symbolic design, we can also flexibly extend our domain-specific language when needed for some more specialized domains. For example, if we add more mathematical operators into our domain-specific language, our model also works on another benchmark called MathQA, where the questions require more in-depth math knowledge, such as in those domains like profit gain, probability, etc. So to summarize, in the third part of my talk, I show that learning symbolic program applications with neural networks is helpful to improve the conversational reasoning of a natural language. At this point, I've talked about my past works on learning-based program synthesis. So here I want to recap some highlights of the contributions. In my work on spreadsheet coder for spreadsheet formula prediction in Google Sheets, I demonstrate the real-world impact of learning-based program synthesis techniques. The main challenges we need to address in this work include the input ambiguity and the large program space. To address these challenges, I designed a neural network architecture to represent multimodal structure input specifications as well as the output syntactic structures. Then in my work on execution-guided program synthesis, I aim to model the program semantic meaning by learning to execute these programs. The challenge we want to address with this learning algorithm is to improve the capacity of programs that can be synthesized, including longer programs and also programs with more complicated control flow structures. Finally, in my work on neural symbolic frameworks, the goal is to achieve better symbolic reasoning and generalization. So to achieve this, the main challenge we need to address is that we want to represent the reasoning process as a program, while we also want to learn to generate these programs without any ground truth annotations. With this discussion of my past work, now I want to introduce my future research agenda. So I'm very excited about continuing working on learning-based program synthesis to bridge the machine learning and programming languages fields. In terms of learning for program synthesis applications, I aim to further broaden the impact of program synthesis with learning-based techniques. Specifically, I plan to design better learning models to empower more real-world program synthesis applications. And again, my long-term vision is to democratize programming for general users with different levels of coding skills. On the other hand, I'm also very excited about working on program synthesis for improving machine learning models. In particular, I plan to extend my work on neural symbolic frameworks to support more open domain learning problems, including those in the domain of natural language processing, computer vision, robotics, etc. So my long-term goal here is to achieve better reasoning, translation, and abstraction for these learning models. And I believe these are also some core challenges we need to address to further advance the entire field of machine learning and artificial intelligence. With this broad picture in mind, now I also want to introduce some concrete directions I want to pursue. So for program synthesis applications, I'm interested in designing an interactive execution-guided program synthesis system to interact with both end users and the execution engine, which extends my work on execution-guided program synthesis. So I believe this interactive design will be very important to allow the generation of customized programs for different user needs, and also to enable more program synthesis applications that might require more complicated programs to achieve. Another direction I'm interested in is common sense reasoning for program synthesis. I view it as one way to reduce the ambiguity of program specifications in some scenarios where the program functionality can be more precise when some background knowledge is baked in the program synthesis system. So to illustrate this point, on the slides, I'm showing some probably funny but actually reasonable predictions for existing program synthesis systems. So assume that they do not have any prior knowledge about the mouses and the states in the US, then both predictions are actually programmatically valid, given only the first line as the input-output pair. So in my future work, I also want to explore how to effectively incorporate word knowledge and allow common sense reasoning for program synthesis, which requires the model to effectively utilize these external resources, both at the inference time to revise the specification and make it more precise, and also to bake in this knowledge in the pre-training phase. Beyond program synthesis applications, I also plan to further scale up neural symbolic frameworks to support more reasoning problems in the wild. This requires us to effectively leverage the advantages of neural networks on learning from noisy data, while we also want the symbolic operators to be general enough to support different problems. Finally, my goal of achieving robust generalization is also connected to my line of research on adversarial machine learning, where my works demonstrate that existing neural networks are vulnerable to attacks, including test time adversarial examples and training time data poisoning. And especially, I show that these models are also vulnerable to these attacks in a black box setting, and also this security stress remain in some commercial machine learning systems. So in my future work, I also plan to explore what neural symbolic design can contribute to make machine learning models more robust and trustworthy. At the end of my talk, I want to thank all my great collaborators from both academia and industry. And also thank you all again for joining my talk. Now I want to have some more discussions and also take more questions. Thank you all.
Thank you, Xinyun. Thank you for the nice talk. I'd like to open the floor to questions now. Let me ask the first question. I'd like to ask about the second project where you showed how without an actual interpreter, you can synthesize some latent semantics, right? Given intermediate states obtained from running the program. So in that setting, you actually do have an interpreter, right? Because you run the program and you do have the intermediate state. You just cannot use it during the execution yourself, but you see the effects of the interpreter. Is that a correct statement? that by observing the intermediate state of the program, say the C program, you effectively are relying on the compiler or the processor executing the program?
Yeah, so the idea for like a C language, for example, is that if the program itself is incomplete, then you cannot directly execute it. So if you want to obtain this intermediate execution states, you need to have some more hand tuning or to implement something to obtain this intermediate execution states from incomplete programs. So basically, the idea is that when we train this model, we only we assume that there's just no information available in this way. So we only use the final program outputs for the full programs, which is, I would say, nearly always available for all the programming languages. And in this case, I want to see whether it can still allows the model to have this benefit of leveraging execution for synthesis.
I see. Do you have any insights into what sort of semantics the model has learned? What does it capture about the execution of the program, and what does it abstract away from?
Yeah, sure. So I would say that definitely with the neural modules, there will always be some errors here. So in the C domain specifically, the model can really learn one or several steps of execution pretty accurately. But when it is longer, then I can see some error compounds. And especially for these partial execution states, for the these if else statements, for example, the ideal scenario is they want to see whether there are some probability distributions of all the possible states in the first step when this branch is not finished yet. So this is something I've been observed when the programs are shorter. But I would say that for executing longer programs more accurately, this problem itself is still challenging, and I'm still thinking about how to really make this learning more accurate for longer programs. Yeah.
Thank you.
Yeah, thanks for the question.
Are there any other questions?
Getting back to your example, to your work on the spreadsheet. So I would love if the spreadsheet could recommend to me the formula that I need to write here, because there is a pretty high cognitive load to write a difficult Excel formula. But the question is, what guarantees can you offer me about the correctness of that formula? Because if I need to check myself that the formula is correct, that might be a higher cognitive load than me writing the formula myself. So this might actually, it's a general question. Maybe you have already the answer to this. I'd like to hear your thoughts.
Yeah, this is a great question. So for these spreadsheet domains, particularly, if you already know what are some values you might expect, so definitely this is something you can check by executing these formulas. But more generally, it is about let's say if you do not want to if you do not have these execution results in mind, then how do you make sure that these programs predicted by neural networks are constructed to be accurate? So I would say that definitely right now with the current learning-based models, we still lack of this guarantee of generating correct programs, semantically correct programs by design. So we still need some other formal methods to prove as the post-processing step. So to having these guarantees in the learning model itself will be a very important future research that I'm very excited about working more on. Yeah. Yeah. Thanks for this great question.
Thank you.
Chen Yu, please.
Thank you for the great talk. So I want to ask about, can you comment on the efficiency or latency of the spreadsheet coder? I feel like the model is kind of big, and then Google Sheet is a latency sensitive application. So I'm wondering how is the efficiency?
Yeah, this is a great question. So this efficiency is also something I've been considering when we design the model. So actually, if we think about the model itself, the parameter set is is pretty small compared to other program synthesis language models nowadays. It is indeed because we want to still make sure that this inference is pretty fast in real time. And also the model is deployed on TPU, so it also makes sure that it can really run in real time. So in general, this model itself is pretty compact, and I would say the synthesis procedure is in general pretty fast. So this is definitely so definitely there have been some, and also for this from the idea of two-stage encoding procedure, because you can imagine that from if we want more full-fledged contextual embedding computation, then we can do the attention over all the tokens, but it will be very slow, as you can imagine. Even with the TPU, it will be very slow. So basically, this two-stage encoding procedure is also one way to make sure that the context is still encoded, while this computation process also will be very more efficient. And also, it can be simpler to really deployed in production. So this is definitely one important practical consideration when we design a model.
I see. Thank you.
Yeah, thanks for the question.
Thank you for the talk, Shin-Yun. If you have other questions, please follow up with her afterwards. And I'll see you later. Bye-bye.
Yeah, thanks everyone. See you later. And if you have any questions, feel free to contact me through emails or other ways. Yeah, thanks a lot, everyone.